Hey guys, welcome to Calculus Day 4. I'll be grading all of you guys' submitted assignments this afternoon. Hopefully have an upgraded grade by this evening. This is due to a couple students requesting that I make sure grades are turned in on Monday because they're having difficulty submitting them over the weekend. And I promised that I would try to help out anybody that could. Once we get more used to the flow of this stuff, I do ask please try to get everything in by my deadline on Friday because I want to start getting grades updated regularly on Friday. That way, people at the Upward Bound office can associate and get in their stuff in on time, because that's part of my job. And if you have something that you want to turn in late, I will accept that still. Just know that until I get it, it will probably be a 0 as of Friday of this week. So make sure I get everything in by my deadline, and Friday evening I will update all grades. So please, please, please make sure we get that kind of stuff in. Okay, for today, we're going to be discussing some key definitions and reviewing a couple of really basic properties, and a couple basic properties that really you may not think of as basic by the time we're done, because you may not have used them in the way we're going to use them in calculus. And so for us, this will be a very interesting day, and I hope it's going to be fun. Let's take a look at today's assignment, and here we go. Kaboom. All right, for today, let's discuss the big thing is we got a bunch of definitions to talk about. Let's go ahead and list them out here. We have function, domain, range, explicit, implicit, and function notation. For each of these definitions, we're going to provide a word definition. Sorry. Monday. Got to talk slower. For each of these, we're going to provide a word definition, which is going to discuss how to put this terminology in the correct context. And then we're going to put in a couple of examples for each one in order to make better sense of how the words actually mean. We will end after function notation by actually doing some math today. Those functions, notations, and these definitions are pretty important. But the big thing we're going to talk about today is how to evaluate, and that'll be our last piece. So, pretty short list. Let's go ahead and get to it. How do we define a function? A function is defined in the following way. A function is a relationship between an independent and dependent variable such that each independent value yields one dependent value. Common ways to write a function would be stuff like, or common functions I should say, would be stuff like y equals x squared. Now that's a function. Another example of a function might be something like the square root function. So y equals the square root of x minus 6, These are all functions. There's an independent variable, which is the x, and that's the common notation, is that the independent is the x. A dependent variable, which is the y, and the important part is the secondary part, which is the part that a lot of algebra kind of tends to ignore, is that for each independent value, it yields one dependent value. Meaning if I pick a number for x, if I say like x equals 2, there can only be a single y answer. Let's call it a. Now, if x is 2, y could be 7, y could be 4 billion. We don't necessarily care what y is as long as we only get one answer. So these are all examples of functions. Some examples of non-functions that you may have seen. A circle function. So the circle function is x squared plus y squared equals r squared. That's not a function. And so even calling it the circle function is kind of misleading. It's the circle formula. Because when you look at the circle formula, it has more than one y value if you plug in an x value. If I plug in x is 2, then it's possible I get more than one answer for y. So this is the idea of a function. And a common part of the function is something called the vertical line test, which we will get into next time when we talk about graphing functions. So look for that next time. Domain. This is the list of all possible independent variable values. In the more common term, this is what you plug in. So if you think of like the table, like you did in algebra, of like, 1, 2, 3, and 4. The 1, 2, 3, and 4, these are your domain. What you get out of them, 7, 3, 1, 3. What you get out is your range. So this is the list of all possible dependent variable values. In other words, this is a list where every possible answer when you plug a number in. So as you can imagine, when it comes to domain and range, these can be big lists. In fact, most often, domain and range contain some version of an infinite list. So like a common domain and range, like some ones you might see are like auto numbers. This indicates that all values are accepted. Meaning every possible fraction, every possible decimal, every possible radical, negative, positive, 0, all real numbers means all values are accepted. Now, explicit versus implicit. Now, an explicit function is where the dependent variable is written in terms of, we put that in quotes here, in terms of the independent variable. Now, this is the most common type of way you write things in algebra. By and far, this is the most common. This is when you have y equals, 6x minus 4. Notice you have on the left-hand side the independent, and on the right-hand side you have the dependent. Notice that the dependent variable is written in terms. Oh, I got this backwards. How did I get those backwards? It must be Monday. Dependent and independent. So your dependent is off by itself. Your independent has all the work to do. This is explicit. It's explicit because y is found directly by plugging in x. There's no solving to do. You just plug it in and get the answer. So like in this case, if I wanted to find out what my dependent value is when x is 1, all I got to do is plug in 1 and simplify. Explicit is the nice one. Implicit is the alternative. These are ones where you have independent and dependent variables interacting. So if you remember back in algebra, things like ax plus by equals c, this was a standard form of a linear equation. And this is implicit, because notice no variable is solved for. X and y have operations between them, right? X plus y, Another example of this might be if you have an even worse version, something like 2xy equals 4. This is an implicit version. Now, It is easy to get from implicit to explicit. All you have to do is solve for the dependent variable. That's how you go from implicit to explicit. However, in some cases, you may want to do this. In other cases, it may be fine to leave it in implicit form. Now, function notation is a specific form of explicit functions. Where in this case, rather than having two variables, you have a functional variable. Examples of this would be like f of x equals 2x plus 3. In this case, how do you define function notations? Is instead of writing y, you replace y with f of x. To make it very clear which one is supposed to be the independent variable and which one is supposed to be the dependent variable. Because if we write it as f of x, then it's clear that x has to be the independent because it's the one that is inside of f. It can't be dependent because it's in itself, it's by itself, it's on its own. And so it's just a variation upon the standard explicit notation. However, this is the one we will spend the majority of our time on. Now, let's get to the meat of today. How do we evaluate a function in function notation? So let's look at a very basic function. f of x is equal to x squared plus 7. So this is a function, meaning that it's a relationship between independent and dependent variables, and for each independent value, it yields one dependent variable, meaning if I plug in 3, I get one answer. If I plug in 5, I get one answer. If I plug in 12, I get one answer. If I plug in negative 4/3, I get one answer. This is a function. So, problems today will ask things like, how do you do f of 2? More advanced problems today will ask things like, how do you do f of b minus 1? The more advanced expressions will ask things like, how do you do f of delta x plus 1? Now, all three of these are asking the same thing, it's just done in a weird way. Let's talk about it. What this means is, this is the function f, where every x has been replaced with a 2. This is the function f, such that every x has been replaced with b minus 1. This is the function f, where every x has been replaced with delta x plus 1. Now, if you've not seen a delta x before, I'll make that note here. Delta x is a variable. It's one variable. It's not delta and x, it's delta x. It's one thing. It is a variable. This means that delta x is equivalent to, like a z or g. Or I had this one teacher who made all of her variables smiley faces because we should smile more in math, and I hated her guts. But it just means that it's a variable. And so you can treat it like any other variable in the problem. So, what does this statement mean? What does f of 2 mean? Well, it means that everywhere there used to be an x in my function, I need to have a 2 instead. So f of 2, in this case, is equivalent to 2 squared plus 7. F of b minus 1 is equivalent to b minus 1 squared plus 7. Everywhere there used to be an x, I replace with b minus 1. So everywhere there used to be an x, I have written now b minus 1. And over here, everywhere there used to be an x, I replace with delta x plus 1. So delta x plus 1 squared plus 7. Now, for these problems, the trick with today is going to be that you need to simplify as far as possible. All right? simplify as much as can be done. Meaning for this example, 2 squared is actually 4. And 4 plus 7 is a number. 4 plus 7 is 11. Meaning 11 is the solution for f of 2. These two are equivalent. Over here, this is where they'll separate out people who remember their algebra and people who don't, because there's often some operations to be done. So b minus 1 squared is an operation. B minus 1 squared is a formula. And so at this point, allow me to point out a couple of really basic rules that need to be applied. Some basic formulas. I'll keep this list going and keep it separate, but these are ones that you need to know. So if I have a plus b squared, you need to remember that this is equivalent to a squared plus 2ab plus b squared. Meaning that no matter what a is, no matter what b is, if you have a quantity squared with something inside, you can always do this. This is FOIL. When people ask me what's something that you need to know well in order to be successful in calculus, this is one of the things. Same with things like the next one on that list. Right? The next one on that list would be a cubed plus 3a squared b plus 3ab squared plus b cubed. And again, you can find that by FOILing. But you need to know that, because otherwise this problem takes a lot longer to do. Because I can look at this problem and do b minus 1 and go, okay, b squared minus 2ab, so that would be 2b, plus 1, plus 7. If you can't take that step on your own, then these becomes very difficult to do. So this becomes b squared minus 2b plus 8. Or in this case, we've taken the 1 and the 7 and put them together to get the 8. And so f of b minus 1 is equivalent to b squared minus 2ab plus 8, meaning I've taken the function that used to be in terms of x and made it in terms of b minus 1, giving me a new function. And over here, the same rules apply, meaning that when I use my shortcut, my cheat code here, if I make my delta x a and my 1b, I would have delta x squared plus 2 delta x plus 1 plus 7. Now, delta x squared is a variable squared. 2 delta x is 2 times a variable, so 2 delta x. And then 1 and 7 can be combined to get 8. So these two are equivalent. F of x minus, or f of delta x plus 1 is equivalent to this statement. But again, all this means is we've taken the function f, everywhere there used to be an x, we replaced with this new value. And that new value can be as complicated or as simple as we want it to be. But you need to be able to evaluate this using algebraic skills. It's one of those kind of nasty parts that makes calculus calculus. Let's do another example. So in this case, I'm going to do an example from algebra again. Let's go with x cubed plus 4x minus 3. This is going to be my f of x function. Now let's look at 3 examples again. A, B, and C. Let's look at A. I'm going to do f of 4x. For B, I'm going to do f of 2 minus x. And for C, I'm going to do delta x plus x. Okay, let's talk about it. What does this mean? It means take the function f, and in that function f, everywhere there used to be an x, we replace with a 4x. What does this mean? It means take the function f. Everywhere there used to be an x, I want you to replace it with 2 minus x. And then simplify. And then here, everywhere we have the function f, take the x, replace it with delta x plus x. So, let's do it. This one. So take the function f, which remember, f of x is equal to x cubed plus 4x minus 3. So everywhere there used to be an x, I replace with a 4x. Everywhere there used to be an x, I replace with a 4x. But what if there was already a 4, Mr. No, I replace every x with 4x. So the 4 out front doesn't matter. It's still there. But everywhere there was an x, I replace it with the 4x. Meaning that when I simplify this function, it is highly possible that you end up with something complicated. And that's okay. Like, don't let that be a deterrent to you. It just means that you're going in the right steps. Now, some will be very simple, like when we just plugged in a number. Some will be more complex, like these three. And the hardest ones will be like C's. And you will have one C for every problem tonight. It does not mean that it's terrible. It means you have to pay close attention and follow the rules. Let's take a look. So here, I would do 4x cubed. Now, when I do my rules, I make sure to use my appropriate power rules. This would mean I'd have 4 to the third x to the third plus 4 times x, which would be 16x minus 3. And then I make sure to fully simplify. 4 to the third is 64. Calculator is helpful there if you don't know. Plus 16x minus 3. So what this is, it's the original function f of x, but I have taken the function f of x and rewritten it in terms of 4x rather than just x. Notice how these two contain similar elements, but they're not the same. You know, there's still an x to the third, but now there's a different coefficient because we plugged in a coefficient. It's still got a negative 3, and that didn't change. But pieces along the way did because we replaced every x with 4x. Let's do the same thing now. Over here. So, everywhere in my function f, where there used to be an x, I'm going to replace it with 2 minus x. Which means, instead of x third, I would say 2 minus x to the third. And instead of 4x, I'd say 4, 2 minus x. Instead of minus 3, well, it's still minus 3. Can't get around that one. Okay, so we've taken this function, and everywhere there used to be an x, we have replaced it with 2 minus x. Now the hard part here is to simplify. Again, these basic formulas, super helpful here, so make sure you have them on hand if you don't know them off the top of your head. Let's do it. So, first one, 2 minus x cubed. I'm going to use this bottom one in order to do that. This would become, let me go off to the side here a little bit, 2 to the third minus 3 times 2 squared times x plus 3 times 2 times x squared plus x cubed minus, then we have the plus 4 times 2 minus x, then we have the minus 3. So let's simplify. 2 cubed is 8. 3 times 2 squared, so 2 squared is 4, times 3 is 12, so minus 12x. 3 times 2 times x squared, 3 times 2 is 6, times x squared is x squared, so 6x squared, and then minus x cubed. It should be the 4, 4 times 2 is 8, 4 times negative x would be minus 4x, and then of course minus 3. And so notice I'm just using properties of algebra. The tricky part is going here. The less tricky part, the part that's going to test how much you remember, is can you plug these in? You know, can you actually get a solution out of this? And so for our final solution, we just combine like terms and get our answer. We have 8, 8, and negative 3. 8 and 8 is 16. Minus 3 would be 13. I have negative 12x. I have negative 4x for a total of negative 16x's. I have 6x squared and negative x cubed. And so this is my solution if instead of having f of x, I have f of 2 minus x. Notice it's a different equation, but that's okay. It's supposed to be, because we're not taking f of x, we're taking f of 2 minus x. Over here, same basic procedure. You would just take f of delta x plus x, meaning that everywhere there used to be an x, are replaced with delta x plus x. Minus 3. And then it's all about, can you simplify algebraically? You know, this will test your algebra skills. I told you guys last week, if you follow my videos, the biggest testament to how well you would do in calculus is how much you remember from other classes. If you have forgotten these basic formulas or didn't learn them in the first place, then calculus is tough. If you remember them perfectly, then you look at this problem and go, oh, delta x plus x cubed, well, I just plug in the formula and I'm done. Delta x cubed plus 3 delta x squared times x plus 3 delta x times x squared plus x cubed plus 4 delta x plus 4x minus 3. And then you simplify, you know. Anytime you look at these functions, like, it's as hard as what you remember. If you don't remember it, then it's hard. If you remember it, then it's just following the rules. Do note the trickiest thing about this is delta x and x are different. They are not the same. Yes, I know they both have an x in them, but 6 has an x in it, and you don't combine 6 and x together. Okay, don't push me on this. Okay, x is not the same as delta x. Don't try to evaluate them like they're the same. Don't try to use power rules. Don't try to use, you know, fancy algebra. Like delta x cubed is just delta x cubed. 3x squared, or 3 delta x squared times x is just 3 delta x squared times x. Like, they don't interact. It's like it's a totally different variable. Delta x is a totally different variable from x. And it turns out, I don't think this simplifies at all, really. Nope, it doesn't. So yeah, this should have been it. As nasty as that looks, it is. But that's what it looks like if you take the function f of x and replace the x with delta x plus x. It's just how it looks. One last thing to point out. It doesn't matter how complicated your f of x is. These rules still apply. So we're going to do one more. It'll be very brief, I promise. Try to keep it simple. What if I did like a trig function? Now, if you haven't taken trig yet, I apologize. We will have a trig week next week where we go through a lot of the trig pieces that you need to know. It's a fun week. But if I ask you to do things like f of 4x, I just expect you to be able to know that it just means plug it in. So this would become sine of 4x. You know, it's the same process, right? Instead of an x, we have a 4x. If I asked you to do something like f of 2 minus x, right? We do the same problem, but with this new function. That means that everywhere there used to be an x, I now replace it with sine of 2 minus x. Everywhere there used to be an x, replace it with 2 minus x. And that's okay to leave it right there if you don't know any trig. It's perfectly fine. In fact, even if you do know a lot of trig, that's usually a pretty good place to leave it. And so if I did, you know, c of f of delta x plus x, it just means that everywhere there used to be an x, and you replace it with delta x plus x. There we go. For some of you, this will be a big test today as to how much you remember from your algebra. I apologize if there's stuff that you've forgotten. We will continue to work on this stuff. We are not going to do something one day and never touch it again. That's crazy. We will come back to this, and we will keep working on this because it's one of those things you need to know if you plan on going into calculus next year. I hope you guys have a good rest of your Monday, and I'll see you guys tomorrow, okay? Assignment will be posted soon. Bye.